Welcome to Chapter 15 on Thermodynamics. We start with the first law of thermodynamics that states that the internal energy of a system equals the net heat transfer into the system minus the net work done by the system. And thermo became a big hot topic during the Industrial Revolution in Britain, where engineers were trying to figure out how to squeeze more work out of the system. You put heat in, how do you get more work and lose less heat? So the internal change in internal energy, delta U, right, is the net heat transfer into the system and minus any work done by the system. Okay, so sign conventions here. If Q is positive, then there is net heat transfer into the system, right? If W is positive, then there's net work done by the system, right? It's very important that you understand that that is by the system, not work done on the system. Work done on the system is negative. Work done by the system is positive. Heat flowing into the system is positive. Heat flowing out of the system is negative. And those are important sign conventions to keep in mind whenever you're trying to solve problems and understand how we're stating thermodynamics here. So the human metabolism is one of those places where we can apply thermodynamics. So we eat food, right? That's a source of energy here. We lose heat, right? Heat goes out, and we do work. Same thing happens with plants. You get sunlight in, you get heat in, you get heat out. You end up using that to process nutrients. So a lot of processes that we talk about in thermo are constant pressure process. So a process by which a gas does work on a piston at constant pressure is called isobaric, right? So constant pressure, isobaric. Since pressure is constant, the force exerted is constant. The force exerted is constant. The work done is just given by pressure times change in volume, right? Pressure is force per unit area. Area times so that times this area, right, gives us the force times this distance. So this distance times the area is the change in volume. So this all works out. Work is pressure times change in volume. In an isobaric process, if we were to draw the curve for an isobaric process, if you will, it's at constant pressure. So if we draw the P versus volume diagram, pressure versus volume diagram, it's just a straight horizontal line, and the work done is the area under the curve. All right, in a pressure versus volume diagram, the work done is the area under the curve. Now that work is positive if the flow is from point A to point B, and then that work is negative if the flow is from B to A. An isochoric process. Choric, you should think, constant volume, right? An isochoric process, we're going to be going vertically, right? Vertically in the isochoric process. So B to C here are A to D, are D to A, C to B. Those are isochoric processes. They happen at constant volume. Because they happen at constant volume, no work is done. All right. Now, if as we note here, if we take and we go from A to D to C, the amount of work we do is right here in this blue area. And if we go from A to B to C, the amount of work done is the purple area plus the blue area. And that's the total area underneath the curve. So there's more work done going from A to B down to C than from A to D and over to C. And it's easy to understand why. Here, you're at higher pressure. And so you do more work moving through the same change in volume at higher pressure than you do at lower pressure. All right, it's like we have a force applied through a distance, and you have a smaller force applied to the same distance. The greater force does more work than the smaller force. So in the total work going from A to B to C to D and back to A is the area then inside the curve. Why is this? Well, in going from A to B, we do the positive work underneath the curve, which is all of this, the purple plus the blue area. And going from C to D, we do negative work because we're headed the other direction, and the negative work we do is the blue area. And so the total work done in going through this cycle is just the work inside the curve, or that purple area right there. So the work done on a PV diagram is and especially if this is a clockwise circle, right, a clockwise movement, the work done is positive and equal to the area inside the curve. Isothermal processes occur at constant temperature, right? Adiabatic processes occur without any heat exchange. And so both isothermal and adiabatic processes are reversible in principle. Right? If it happened at constant temperature in principle, you can go back the other way along the same isothermal line. Or if it happened adiabatically, in principle, you can go back along the same curve. So for a process summary, we have isobaric, constant pressure, W equals P delta V. Isochoric, constant volume, W equals 0. Isothermal, constant temperature, the heat flowing in is the work. And adiabatic, there is no heat transfer, and so the heat flowing in is 0. And that's it for this section of the lecture on the first law of thermodynamics.